I think now is a good time for me to ask you a philosophical question. How many unknowns are there in a problem concerning fluids? How many variables do we need to solve for in order to, get a full picture of what's going on in the fluids? Well, first, the UI, the velocity on 3 directions are unknown to us, right? This we need to solve for. This gives us 3 unknowns. And we have more. The sigma tensor, the stress tensor, the Knight tensors are all unknown to us, right? So at least we have, say, over 10 unknowns. Do we have that amount of equations? Of course we don't. How many equations do we have? You can say we have 4 equations, right? First equation is the continuity equation, and the other 3 are momentum conservation equation on 3 directions, respectively. What will be called NS, Navier-Stokes equation, shortly. But we only have 4 equations. There are so many unknowns. How can we solve for them? Well, luckily for us, not all those variables, not all those unknowns are independent, right? We can represent some of them by some of others. So how many independent unknowns do we have? One way to define that is like this: uj, that gives us 3 variables, right? Or you can also write ui. And another one is called p. Do you remember the p? What's the difference between this p and the pressure that appears in the stress tensor? You can say the minus P11, minus P22, minus P33, they are actual pressures, right? But this P is the hydrodynamic pressure. Here, we can call them to be the pressures in the dynamic case, right? So actually, we can get all the other variables in here and in here by using these 4 variables. So actually, one way to put it, we only have 4 independent unknowns, which are the uj and the hydrostatic P. Another way to put it is, we see there are indeed some independent stresses. Not all stresses are independent. Say minus P11, minus P22, minus P33, tau 12, tau 13, tau 23, tau 21, tau 31, tau 32, right? Not all of them are independent. Actually, you can say only 4 of them are independent. This tensor has a very special property, which is it's symmetric. That is, tau 12 equals tau 21, tau 13 equals tau 31, tau 23 equals tau 32. This is the same result as in solid mechanics. I guess you are familiar with this notion, so I will not elaborate on this. So these 3 tensors, these 3 stresses are indeed independent. So another way to express or to state what our unknowns are is to say the 4 unknowns are tau 12, tau 13, tau 23, and another pressure. Here we can use a pressure called the dynamic pressure. We know that the P11, P22, P33 can be different from the hydrostatic case P, right? But there is some invariance in them, which is PD. We can define it to be 1/1/3 P11 plus P22 plus P33. This thing does not depend on how we define the coordinates. So we have this cube, right? it's P11, P22, P33. The sum of it will equal to, if we still pick this point, but define the coordinates another way, maybe x, y, and z, something like this, right? So no matter how the coordinate system changes, the sum of the three pressures doesn't change. So we can use this as an invariance, right? So this is the real, how can you put it? The real index of the pressure at a dynamic case, right? So we can call this to be the dynamic pressure. So these are the two popular ways to express what our unknowns are. Keep in mind, we have 4 unknowns, right? And we have 4 equations. So the system, the whole system, is actually a closed system, although it may be very hard to solve for them, right? We know NS equation is very hard to solve. Well, okay. So now let's talk about how, well, we haven't gotten the NS equation yet,